Right, in this video segment we're going to get into a little bit more depth about simple tension tests and the data that we collect and the basic information that we're going to get out of that. Along the way we're going to more precisely define things such as normal stresses, normal strain. So in this image here, and you can see these kind of pieces of equipment in grander detail in those video links that were provided. Note that we've got these a lower jaw here, upper jaw here. Here's our test specimen. These are sometimes round bars and sometimes they are flat rectangular bars. Depends on the material and the standard at which by which you're conducting the test. We just have data logger equipment over here. This is all computer controlled. Right? And what's going to happen here is that when the test goes, we're going to then have either hydraulic or screw-driven system that is going to take these jaws and pull that material apart. Up here you see this big sort of thick cylinder. That is actually the test cell, the loading cell actually, that then sends electronic data over to our collection equipment. Right? So what we're trying to do here is ultimately develop the stress-strain curve or behavior of this particular material. And the way that we do that is by imposing forces, not imposing stresses, but imposing force. So this load cell is going to collect how much force we're imposing, and then over a special location, which is called the gauge length, and that standard would typically be 2 inches for most metals. Then we'll have what's called this extensometer. Now in the old days this would be a little physical piece that would be set up and have armatures, and there would be a little dial gauge, and as this bar elongated it would move those little bars and it would cause the dial gauge to move around. Now we do all that same work with electronic equipment as opposed to this mechanical piece, and the only difference in terms of quality is that we can more easily record the data. The data itself is no more or less accurate as a result of being digital versus analog, right? And so this thing is going to elongate under this load as we continue to do that. We're going to look at this narrow section and we'll eventually be calculating stress, that force over the cross-sectional area. We'll be looking at the strain that happens, the amount of elongation that happens over that 2 inches. So if that were a standard test for metals, that would be that little delta over that region. So there's your little delta, that elongation as that thing stresses out, right? And so you can ignore this for now. We'll get into that in just a second. Now again, the data that's actually collected is not stress and strain. It is instead going to be force versus deformation, the total amount of deformation over that special length, that gauge length. And when you do that, particularly for say a low carbon steel, the kinds of magnitude of force that you're going to see under your typical specimen are going to be on the order of 10, 20, 30,000 pounds of force. Right? So very large forces. Now, of course, the scale on this that we're going to have, the more material in the cross-section we have, then these will go up, and we want to make that sort of more non-dimensional. That's why we're going to go down, and we're going to look at not the total axial force on the member, but we want to convert this to stress. How is that force spread out over the cross-section? Right? So I'm going to draw that stress distribution off to the side to make it a little bit easier to see the deformation drawing that we're going to do. And if we're away from these edge effects, or the dog bone is happening, then we will end up with a relatively uniform stress field. And that relatively uniform value will be then our axial stress, or normal stress, is equal to P over A. Right, so that's just that intensity of the force. That A would be the cross-sectional area, and there's your sigma for the normal stress. Now how much this thing elongates then is also of particular interest. Now the delta that's measured up here is over the gauge length of typically again of 2 inches. But as this thing elongates down at that micro level, then we might look at this like so. right? And usually most materials, when you stretch them in one direction, they'll actually shrink in the other. That's the Poisson's effect. We'll get into that in just a little bit. If we started off with a length of dx, then we have to shift our axis a little bit. There's our dx again, and our total elongation, because we're at the incremental level, we'll call that d delta, is going to be of a critical important kind of value. Right? Now, note that little d delta in this case happened on both sides outside of that little dx. I just shifted it all mathematically to one side to make it easier to see. This thing we call strain with lowercase epsilon is capturing this for us, that it is the amount of deformation over that original length. At the incremental level, that's d delta over dx. At the more macroscopic level, the way we collected it up here in this chart, that would be that total amount of deformation over that original gauge length, which again is usually about 2 inches. This viewpoint of the little Greek symbol sigma and real Greek symbol epsilon is now, in a sense, it's not really non-dimensional. It has units, right? This is units of deformation over units of original length. And you say, well, that will cancel out. Well, it kind of does, but you got to get that you have units of deformation over units of original length, and of course stress is going to end up with units of force over area, or length squared, for its units. So it's not really non-dimensional, but it is unitized down at this micro level, as opposed to, and it removes the problem of testing different specimens that might not have exactly the same cross-sectional area. We would not be able to directly compare this kind of a plot. We though can take that and put it into then the stress strain curve, which then we can do direct comparisons, and you'll see that in just a little bit. Right, so we've got stress on one axis and we have strain on the other. And before we go into the individual properties, just want to kind of point out here some of the basic key features that we tend to see. This is an example of a low carbon steel. We oftentimes will have some sort of a linear elastic region, some sort of little bump in here that completely goes away from linear elastic, and that's called the yield point. And then you end up with sometimes a flat plateau, plastic plateau we call it. And then we'll have what is called a strain hardening region. This region, because of what goes down at the microstructure of the steel, will actually pick up stiffness again. We'll reach some sort of hilltop, and then we'll have some sort of rupture or failure. Not all materials are going to be like this, not all metals are like this, and not even all steels are like this. But there are these key features usually of some sort of a proportionality or elastic region, we call it in here. We'll have some sort of yielding, we hope, and some sort of peak, and then eventually some sort of rupture along the way. In our next video, we'll get into in detail what some of these properties are.